So it has been a year almost. Oracle launched its managed Lustre service. So since then, we have very large file systems running in the cloud. Some of the large file systems are running in OCI cloud, and customers are using it as managed file system. What we are going to do today here is that we are going to share our experience running the managed Lustre service. What is special about managed Lustre service is that customers go to the OCI console. They create a file system, provide a file system name, the size, performance tier, and also a network, which is very important. They provide a network where the Lustre file system will be attached to, and click create. They can also use Terraform, CLI, API, whatever the modes. Once it's created, customer can go and mount the file system, and their job is done. They can start using it. The service provider, OCI, on the other hand, do the heavy lifting. We provision the file system, we maintain the file system, we do all the operational aspect of the file system. So that is basically the managed service, taking all the pain away from the customer. The managed file system concept in the cloud is not new, so it's not cutting edge technology. It has been there for a while. Many cloud providers have done it. However, what is special today is that we are going to share that experience, what we have, what we learned in the last 1 year. So here is an agenda today. I'm not going to go too much details into it. Basically, we will go through some architecture things, and then we are going to show a practical file system that is created as a managed service file system, and then some key architecture decisions and what are the operational challenges we faced. That's pretty much it for today, and we'll just talk about, in this slide we talk about what are the challenges that we usually face in cloud deploying a Lustre service. Cloud is easy for customer. It makes it easy for customers to consume resources. They can easily provision. However, as far as Lustre is concerned, cloud is a little bit different from the on-prem, HPC clusters that we have. Mainly, in the cloud, what we have is general purpose compute instances. By the way, there is other type of shapes available, like we just got RDMA and InfiniBand and things, but we are not talking about that. But the general purpose instances are mainly ephemeral. What I mean is that the hardware behind these instances can get replaced, rebooted, maintained, patching, maintenance, everything can happen. So you don't, as a service provider, the compute team actually goes and does this, and you don't have much control over it. So that means, it's sometimes it's out of your hands, basically. And then, on the other hand, on the on-prem, you're going to have like dedicated custom-built hardware, which are interconnected using InfiniBand, low latency, that can give you single-digit microsecond latency. On the other hand, on the cloud, it's not that the case, because cloud has got regions and availability domains, availability zones, whatever you call, and it's going to be span across buildings, and you're going to get latency like 100, 200 microsecond latency. So there's a big difference in latency between on-prem and cloud. And the consumption model is also different. We have a multi-tenant concept in cloud where multiple customers. So this is not Lustre multi-tenancy. I'm talking about multiple customers consuming resources. It's a little bit different from the Lustre multi-tenancy that we covered in the previous presentation. And of course, in on-prem, you have predictable maintenance where you own the entire infrastructure, so you can actually control when the maintenance is going to be done. But in the cloud, it's not the case. There's going to be maintenance notification and things, but it's not really fully in your control. we have talked most of this in the previous slide. So what I'm going to talk about is basically the metric. So Lustre provides a lot of stats, but it doesn't give a method to consume the metrics. So that is a cloud provider job where, take the metrics from the Lustre file system and put it in a place where customer can consume, visualize it, and all those things, right? And since we have, can have thousands of OSTs in a large file system, it can become a scale problem. So that's another challenge that we got to face during, implementing a managed file service. And these are some key design decisions that we made. We are going to have separate slides for each of these, but I'm going to pick a couple of topics from here. One is we are going to use overlay networking from managed service. It's because it's easy, it's virtual, and it gives a lot of flexibility about creating subnets, destroying subnets, attaching VNICs into your subnet, different VCN. VCN is actually a virtual cloud network, that OCI term for a virtual network. So you can actually do VNIC attachment into different VCNs. Not only in your tenancy, you can also have this VNIC attached to other customers' tenancy as well. That's how the multi-tenancy is actually implemented in cloud, by the way. And also I want to talk about the API-based provisioning. So all the resources that the cloud provider provisions for the managed service is actually API-based. We are not doing anything special. We use whatever the external API available in OCI. We just use that. And we have a separate slide that demonstrates how we actually concurrently use these APIs to provision file system very quickly. So this is a overall architecture of the managed Lustre service. So basically on the top right-hand side, you have the user sitting. They are going to do create, delete, those CRUD APIs. And it hits the OCI API gateway, it does the authentication, authorization, and all those things. And then it will call the upstream service API, which is basically within LFS. LFS is nothing but Lustre managed service by OCI. And that is basically has the business logic to execute that API. So it could be a create file system, delete file system, manage, modify file system, any of those type of APIs. And then we rely on Lustre management plane, which is kind of the heart and brain of the managed service, where it does most of its job. Basically, it does the heartbeats for the Lustre DP host. It does the workflows, failovers, provisioning resources. All those things are done by management plane, and it's the heart of the management service. And on the left side, what we have is a Lustre data plane. You have multiple file systems as customer create. More and more will appear, and they all appear, all those OSs, MDS, all those things appear in LFS tenancy. But at the same time, what we do is we actually attach a VNIC into customer managed VCN so that the customer can go and mount it. So it becomes reachable from their network, although the file system is sitting in Oracle tenancy. And bottom, we actually use Oracle block volumes. And also we use Oracle telemetry as well to push all the Lustre matrices. So what I'm going to show here is that this is a practical or real file system that is created in cloud using OCI. So on the right-hand side, we have a screenshot of a file system. Basically what it tells you is like the size of the file system, what is the performance tier. So here the performance tier is 1,000 meg per terabyte, and it's a 1 petabyte file system. And then you also have details like, which network it gets attached to, and from that network or the connected networks, customer can go and mount the file system. And on the left-hand side, I put the configuration. It's basically not visible to the customer, like the number of OSs being used, all those details is not available to the customer. They can kind of figure it out, run LFSDF, figure out how many OSTs are there, and all those things can be done. And this can actually change the size and performance matters as long as we deliver the performance tier. Whatever we say we perform, which is 1,000 megabytes per second per TB. And we took this file system for a benchmark run, and then we can actually push more than 1 terabytes per second in cloud with 1 meg IO size. And I have used 44 to 100 gig NICs. What that actually means is that like we could saturate the clients almost 200 gigabits to get that 1 terabyte throughput. And also at the same time, we are using 100 gigabit NICs for the Lustre servers. We are actually doing 10 gigabytes per second per server as well there to get to that 1 terabyte per second throughput. And from the metadata perspective, we can actually achieve more than 1 million creates per second, more than 1 million deletes per second. We also have per MDT as well, like we can achieve 200,000 creates per second and so on. And now we'll talk about some architectural choices, how we achieve high availability. So for volume durability and performance, what we do is we use OCI block volumes because that is a proven technology for OCI, and it is actually protected by SLAs. Like you have both performance and as well as availability SLAs available to the block volumes. And you could have iSCSI or NVMe attachments, and it's predictable performance. And of course, these volumes will be moved around across OSTs. So we need IO fencing, so we use iSCSI 3% persistent reservation. And on top of that, we also have the ext4 multi-mount protection. And more importantly, we provision, our provisioning is fault domain aware, which means that the power domain for the resources that we provision is across different fault domains, so that if there's a top of the rack switches or there is a power failure on a rack, the other fault domain actually can take over. And again, continuing with high availability, what we did is that we actually use 1 IP address per Lustre target, MDT, OST, MGT. And with the virtual networking that we have, we can actually move these IP addresses within sub-second, like within few milliseconds, we can actually move IP address from one place to another. And what we do is we actually first fail over the volume, and then we fail over the other way. I think we first move the IP address and then we move the volume. Some trade-offs we have to take, like we have to disable multi-rail to make sure that the clients don't discover any needs on the server that it's not supposed to. So we disable that as well, and then we also disable import from loopback. So the reason is that if you have 2 MDTs running on the same MDS, we don't do that. We do 1 MDT, 1 MDS, but sometimes during a failover scenario, you could have 2 MDTs running on MDS. So each other can actually discover or import each other using the loopback. And the problem is that when MDT moves from that system to another system, for some reason it keeps hanging on to the loopback import, and it never gives up. So we make sure that by disabling that loopback import, all the targets gets imported by the IP address. And this is how we achieve multi-tenancy. When I say multi-tenancy, it is not the multi-tenancy, Lustre multi-tenancy. It's basically, in the previous presentation, I think it was called multi-single tenancy, where every customer will have their own OSs, MDTs, and MGTs. The way we achieve is that by 2 techniques. One is that we do cross VNIC attachments from one tenancy to another tenancy where the customer is running, so that the customer can reach the file system. That is one way we do it. And the other one is that we use Linux network namespaces. We put all those OST IP addresses in the Linux network namespace, and main advantage behind that is that we can like customer can have their own IP space. They don't have to worry about what IP space we use in OCI. So there is an isolation there. And since we use VCNs, customer can actually use the VCN features like, security group, security list to, secure traffic within or outside VCN. And this is how we achieve low and predictable latency. Like as I mentioned, in an availability domain or availability zone, you have multiple buildings and you can have higher latency. Sometimes it's variable as well. So what we do is we have a concept called cluster placement groups. Customer create a cluster placement group and they pass it so that all the resources provision for the file system will be from the same room or same building, so that the latency across that will be very minimal. And it will be less than 100 microseconds. And the same cluster placement group can be used when the customer create their Lustre clients as well, so that the Lustre client also sits near to the file system. And this is one of the things we talked about, how we do telemetry. So the Lustre provides a lot of stats, and the metrics are not as simple as like you have metric name and a value. It's not that simple, right? So you have something called a dimension or a label, which actually explains what that metric is. For example, if an OST is emitting a metric, it has to tell what OST name it is. And if it is from a particular client, it has to tell what client it is. So every metrics actually comes with something called a dimension. And this dimension, we have to be careful that the dimension can have a lot of values. Like for example, client IP address. It's a big thing, right? Like you can have thousands and thousands of client IPs, client user IDs. It's an unbound dimension. So those things we have to be careful so that, I put a math here. If you go with that math, it's 80 million, and then that's one metric. For example, read bytes. Write bytes, you're going to have another 80 million, right? So what we do is we have to be careful that we don't emit unnecessarily dimensions that has got unbound values. And also we have to take a distributed metric emission strategy because that is what scales better. We don't want to coordinate. We don't have a single emitter that emits the metric, so that the coordination is very tough. So every OSTs that will produce metrics and send it to the metric telemetry backend. The problem is that this metric telemetry backend, they are actually responsible for every service, not just for LFS service. It's a common telemetry backend for the entire OCI, and other cloud providers also will be similar. So there are limits, capacities, and everything involved. So we don't want to send too much. Only send what is necessary. Also, the emission frequency is also important. So we do one per minute emission so that the customer can actually almost get real-time monitoring for their workloads. So those are the considerations that we made for emitting metrics. And this is another thing, maintenance, how we do maintenance. So there are some features we discussed yesterday, I think. There is a quick, Lustre recovery mechanism that is being developed. But today what happens is that when a failure happens, the OST has to recover on the new server. And it takes time, and if you have malfunctioning clients, if the client doesn't come back, it has to time out, and it could take minutes. In our testing, we tested with more than 4,000, 5,000, clients, and the recovery can happen within 40, 50 seconds. But there are situations where it can take time, right? So for a long-running workload, this much time may not be, this is a pause, it's not an error situation. So that much pause for a long-running workload may not be a problem, but there can be sensitive workloads, right? So that sensitive workloads can IO timeout, error out, and then application crash, right? So in order to prevent that, we actually give maintenance window to the customer, and this maintenance window is actually configurable by the customer. They can pick which day and time they want to do maintenance. And also they can actually override the next maintenance as well. Like for example, if there is a maintenance schedule for Sunday, they can go and change that as well. So it's customer configurable so that they get a kind of a smooth experience and much control over how we do maintenance over Lustre file systems. And that concludes my part of discussion, and I'll invite Sonia to do the operational issues with Lustre.
Yeah, thanks, Aboo. So I'll not take too long, just quickly go over some of the operational issues that we experienced while running this managed Lustre service in OCI. So the first one, so what we see is that some of the customers, they have the workloads which are heavy metadata workloads running. And the problems that we saw with that is that sometimes we would see that, with these heavy metadata workloads, the MDS server nodes, they hit a wall, and they basically, their CPU, they reach the CPU and the memory limits, and what it leads to is that it can lead to concurrent failovers of the MDTs that are mounted on that MDS server nodes, because MDS would stop heartbeating. The management plane in OCI, it captures the heartbeats to make sure that the server is healthy, but because of hitting these CPU and memory limits, the heartbeat is not there. Management plane will think that MDS node is not healthy. It will try to move the targets, and that is not a good experience, because when we try to minimize these failovers, especially for the scenarios which are not really related to the real failure situations. So we try to use some system settings like CPU partitioning to ensure that some CPU cores are dedicated only for the essential heartbeat mechanisms that we have, and for the server health itself, apart, and the rest of the cores can be used for the Lustre workloads that are running on that server, MDS server. We also tuned the killer so that we prioritize not to kill these essential critical system services. But one more thing interesting that we observed is that there was with the default settings in Lustre, there was a active massive buildup of the logs from these clients on the MDS nodes, and so that was also one of the contributing reasons for these the MDS nodes reaching these system limits, because then these log cancel operations, they were consuming all the CPU cores on those nodes basically. So we tuned, and with some testing and everything, we found some optimum value for these settings, and we implemented those in our in all our file system deployments, and that helped. Yeah. So the next issue so traditionally, right, in these lab or Lustre deployments, we usually just leverage to serial mounts of the targets. Like we mount MGTs, we mount MDTs, and then we mount OSTs, and then eventually the client nodes can mount the file system. So initially when we launched the service, right, serial mount was fine because customers were just onboarding and deploying smaller file systems. But as they scaled, as they started deploying multi-petabytes file system, right, this serial mount didn't scale. And of course, in our management workflows also, there were some paths where we were leveraging only the serial provisioning or those things. And basically, if I give you an idea of a 20 petabyte file system deployment would take somewhere around 12 to 15 hours easily, which didn't seem to be a good experience. So we thought of just leveraging parallel mount. And initially we thought, okay, let's just mount everything parallelly. But of course, we hit some Lustre bugs that when we mounted all the OSTs parallelly, the MDS node started crashing. And I'm not talking about the MDT parallel mounts here, but we saw some issues with that also. We had a workaround where we just mount MDT. We make sure that MDT 0 gets mounted first, and only then the rest of the MDTs. But by the way, this is specifically about the Lustre 2.15.5 servers. The fixes have landed for the MDT also, parallel mounts also in 2.16, because I tried those fixes, and then like we didn't had to really had that workaround of always making sure MDT0 goes first. But I'm like the issues that I'm covering are specifically for the 2.15.5 LTS versions. So, but these fixes, thanks to Alex, like they worked, and like they worked really well. So this is the time that we reduced for leveraging the parallel mounts. It got reduced to just like 23 minutes for a 10 petabyte file system. And you can see out of those 23 minutes, 17 minutes is basically the provisioning time that OCI, our workflows takes. But we reduced even that provisioning, like we changed our workflows in a way that also reduced to like, this is almost like, 2,500 OSTs and somewhere around 200 OSS nodes. So with that, like earlier it was, for 10 petabyte file system, it was around 10 to 12 hours, which got reduced to this 23 minutes. So that was a massive win for us and for our customers. There is one more, yeah, this is interesting. So this happened with a very large customer, critical customer, but thankfully we were just running kind of a POC, and before they fully onboard with us, they were running some workload over a period of few days, and they encountered this issue over a weekend that they reached, they were able to manage to just fully saturate some of their OSTs, like they were like 100% full. And with that, they hit a kernel bug, they hit a Lustre bug, again 2.15.5 LTS version. They hit a Lustre bug that basically crashed some of the OSS nodes where these full OSTs were mounted. The problem was not just the crash, the problem was that once the OSS node crashed, our failover mechanism would kick in, would basically just mount the OST on a different failover node, but now we could not even mount it back. Those OSTs could not be mounted back because there was no space at all, even for the config logs to be copied over to those OSTs. So at that particular time, we didn't want to delete any files because this was like customers' data and everything. We didn't want to play around. We just expanded the LDiskFS space. OCI has that, those block volumes, they have that capability. So we expanded, and we were able to mount those OSTs back. But then during that learning, we also realized that maybe we can play with these reserved MB low and reserved MB high settings to make sure to have a higher threshold before reaching the OST full. But this is not, again, complete solution, because these settings, they only help for the pre-create scenarios. Like, when MDETs, they are basically pre-creating some objects on the OSTs. So when customer is running workload, even if your OSTs are hit that threshold setting by reserve MB low, reserved MB high, so MDTs will not create new objects on those OSTs. But the customer can very well expand the existing objects that are already created. So append to them, and some in-flight writes which were committed to those OST would also just keep on going, which eventually can just cross the threshold and still make the OST full. So we took some fixes. The first fix was definitely the main reason that the crash happened, so we had to take that. That helped. Okay, if OST is full, we might not crash. We will not hit the bug and we will not crash. But who knows? Some other day there could be another bug that can crash the node. So eventually we would want to find a solution where if we have defined a threshold, then we never cross that threshold and reach the full OST conditions. The second LU 14714 helps in the scenarios even if the OST is full and we have hit some kind of crash or something and OST got unmounted, we can still mount it back by not copying the log config from the MGS to the local, because we cannot copy because the OST is full, but at least the mount would go through. But still it will be at the full capacity, and somebody needs to tell the customer, or some operator needs to come in and clean up that OST, do a LFS migrate or something needs to be done. So So far, I think there is no foolproof mechanism in Lustre which can help me that if I set a threshold that I don't want any client or any customer workload basically crossing that threshold to reach the full OST capacity, then I can do that. But yeah, I think we can talk about it more with some Lustre experts and see if it should be done, if it's feasible, those things. The next slide is, so one of the things that now that new and strategic customers are coming in, wanting to use this managed Lustre service from OCI. And these customers, they want to run their AI/ML workloads on 64K ARM GPU nodes, which are very popular anyway. And they are also very performance sensitive. So they want to have the direct IO performance, let's say, right? They don't want to compromise on that. So, but we were running Lustre LTS 2.15.5 version. And along with these strategic customers, we have a diverse customer base, right? Running different Lustre client versions. So OCI as of now is not handing out the Lustre client builds. Customers can choose what version they want to use and what kind of nodes they want to x86, 64K ARM or 4K ARM or whatever, right? So we thought, okay, to help with these strategic customers, we can maybe try to backport this UDIO feature, thanks to Patrick and so many others who worked on this. So we were able to backport. It was like massive backport, but we were able to backport it, and our customers were happy using it. Some of the customers, they had to take some extra patches in their client versions, but more or less like our diverse customer base is happy with, and plus it helps us running single server image, right? We don't want to like running different server images for different customers, so running different client versions. So as of now, this is recent, so as of now, we were able to like make all our customers happy with this. There are some known bugs already, especially with the Lustre 2.17 client, and I think it's actively being worked upon, but it's like the fixes are layered. It's not like a simple solution. So, but so far we realized that if we just disable hybrid IO, then it works perfectly fine. Yeah, I guess that's it. We have had other operational challenges, but like, I think for this presentation, this is enough. These are some just key learnings, and yeah, it's been 1 year now, and we acknowledge the support that we receive from VAM Cloud and the Lustre community in general. Yeah, thank you.